number 4 for oscillations. My name is Nolan Charles, and this is for the class of Physics 2211. The focus of this lab was to examine the oscillating motion of a spring mass system by analyzing the video data on the right and comparing it with a computational model that we would code in GlowScript. The computational model is based off of Newton's second law, where we found the predicted motion through the derived velocity update formula. Our object was the weight attached to the spring. Our observed motion was found through Tracker, and our predicted motion was found through GlowScript. The fundamental physics principles involved are listed below. First, we use Newton's second law, which relates the net interaction between a system and its surroundings to the observed motion of the system. Next, we use the first law of thermodynamics, which states that energy is neither created nor destroyed, but can be transformed or transferred. The formulas listed under Newton's second law is what we use to update the velocity and to predict the motion in our computational model. And the formulas that are listed under the first law of thermodynamics, we changed to be the change in E is equal to the change in kinetic energy plus the change in potential gravitational energy plus the change in potential spring force energy. The derivations of each of these individual components are shown on the right. We use these in graphing the total energy. The steps that we use for this lab are shown on this slide. Step 1 was to analyze the video in Tracker. This yielded data that we put into a CSV that we could upload into our GlowScript code. Next, we made a computational model. This model shown right here is the first part of it, where we are setting the initial values. Next, we graphed the energy changes as well as calculated the velocity update and position updates. And in doing this, we were able to generate graphs that we can use to compare our results. The image on the very left shows the diagram that was made of what the predicted motion would be. The middle graph shows the changes in energy, all the different types of energies. And then the two graphs on the very right show the differences in the x's and the y positions of oscillation. For potentials of human error, my biggest source of error would be when I was tracking the motion on the Tracker program. You have to be very precise in where you're clicking, and there could have been potential error there. For our what-if problems, the first problem is, what does it mean? It asks for your model system, is the energy principle satisfied? I would say that it is. You can see this through our graph that is shown below. The orange line represents the total change in energy over time. This line stays very close to zero throughout the motion, which indicates that the total energy is conserved. Although the kinetic energy, the blue line, the gravitational potential energy, the red line, and the spring potential energy, the green line, all vary periodically, they all signify how the energies should balance each other out. As expected in a conservative system, energy is continuously changing between kinetic and potential forms, which confirms that no external forces like friction or air resistance are modeled, and also confirms with the first law of thermodynamics, as mentioned earlier. This is exactly what we should expect in an ideal spring mass system. And the nearly flat delta E curve, or the total energy change, supports that the simulation obeys the conservation of energy principle. For our last what-if question, it asks us to compare the x and the y positioning of oscillations. In order to do this, I did a rough little calculation where I would calculate the distances between the troughs. The average trough for the x positions was about 1.65 seconds, and the average trough for the y position was about the average for the x direction was 1.68, and the average for the y direction was 1.65. This tells us that the system's motion in both directions are nearly synchronized, which is what you would expect in a spring mass system undergoing this kind of oscillation. If they weren't synchronized, this would point to some type of error on my end. Thank you for watching.